All right. So people ask me to talk about open Petri nets. So I'm going to talk about my recent paper with John Baez, which is called Open Petri Nets. So it is about open Petri nets. And stop me if I ramble too long about something, because it's helpful, actually. OK. OK, so in our paper, we're really, I guess, all right. We're really doing two things. Has two main goals, which is to make a double category, or make a category of open Petri nets. And then the second thing is we want to describe reachability as a functor from that category to relations. OK. And I don't know if you guys want me to talk about like the motivation for this. I think you guys got that covered. So I'll just describe what it's about. OK. I'm going to write functor for now, because it's not actually a functor. And you'll see. OK. So I guess just for like the purposes of, so really we start with a category, or we can do a category, but what we really did is we did it in more higher category language. So we have two cells. We did a double category of open Petri nets. But it can reduce to a category if you take all of the horizontal things to be identity. And you also don't care about, well, OK. You choose push-outs. If you're careful enough, you can make it into a category. You choose push-outs for every diagram. Then you can get a category. OK, so and I'll describe that as, I guess, should I just do the double category? Yeah, you guys want that. OK.
Should we double category and not bi-category?
Yes, I mean double category.
Sure. OK. Will you please describe it?
Mm-hmm. OK, so we call it open of Petri, which suggests that it depends on Petri, and it does. So our category of Petri nets, just to make sure we're on the same page, is different from some other papers. So Petri has objects the regular Petri nets.
What's the regular Petri net?
Yeah. I think of them like this, or we think of them like this, as two maps from some transitions to a free commutative monoid on species. Source and target maps.
What does regular mean? Regular doesn't mean.
Not anything, just like the definition that other people use. Yeah, that's what we regular. Ordinary. Yeah, OK. Stable under push-out. That's what, no. OK, but here's the change is that we require the map between the species to come from a map between the species, the set of species, and not be an arbitrary monoid homomorphism. I think, Pavel, you did that in one of your papers. I think your reachability paper, maybe. This is the type of morphism used. But Sassoni and a lot of the classical references use, let this be an arbitrary morphism. And also, the source and target maps commute. So I guess so if you do S and then N of F, that's the same as doing G and then S prime. And then similarly for the target maps. Right? OK, so that's Petri. All right, so then open of Petri. I guess I'm not going to tell you what a double category is. You'll just have to, if you don't know what it is, then you'll have to like guess from what this category is. Well, OK, so the idea, if this is a terrible explanation, but like if you want a quick PIV explanation, it's a category internal to categories. So you have a category of morphisms and a category of objects, and then composition is a functor from the morphism category times itself to itself. So you specify vertical morphisms, and you specify horizontal morphisms, and you specify squares or two cells, and then they all have their own compositions, and they play nice with a bunch of coherence axioms. Okay, so I'm going to call them 0 cells. 0 cells are sets. Any sets, not necessarily finite. Okay, horizontal 1 cells. These are the open part. This is the open part. These are going to be cospans. Oh, wait. Yeah, okay. So horizontal 1 cells are cospans like this. Okay, in the category P-tree. So these are morphisms of P-tree nets. And I'll tell you what L and X. Okay, so L of X, L is a functor from set to P-tree, which takes a set and turns it into the discrete P-tree net with only that set of species and no transitions. And then you could probably figure out what it does to morphisms, to functions. So right? That makes sense? Okay, and this is a left adjoint. Okay. I'll write that.
Because left adjoint,
Yeah.
that just forgets the transitions.
Yep.
Or returns the set of species.
Yep. Right. Okay. Okay, so what's going on here is you have two P-tree nets which just have species, no transitions, and then you're mapping them into a full-blown P-tree net with everything, and it identifies sort of input and output nodes or species of your net. I use species instead of places. Is that confusing to anyone? Okay. I'll try to say places because I'm in a computer science context. Okay. 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 So that's the 1 cells. Okay, and then vertical 1 cells. Anyone want to guess what it should be? So it's not going to be morphism of Petri nets. Yeah, it's going to be functions. Yeah. Right. So they are morphisms of Petri nets, but because in Petri we require them to come from functions, it's more straightforward to think of them as functions. So like something like that. Whoops. Prime should go in there. And then L of F. Well, actually, yeah, in general, you should think of them as functions for other open networks like this as well. Okay.
Sorry, can you tell me again, P in the middle is not is a Petri?
Yeah, it's any Petri net.
Okay. But then, and the F from L of X to P is a Petri net morphism, or?
Yes, it is, LF. So if you take a function between sets, you can get a function.
Yeah.
Mm-hmm.
Doesn't have to be injective.
No, it doesn't. Right, so it's probably useful to draw a picture. Where should I draw it? Draw over here.
So another way of describing this is you can take so Petri is a co-complete category, finitely co-complete category. You can take the double category of cospans in that, and you take the full sub-double category where the objects are the discrete Petri nets.
Yeah, essentially, you need this to be a left adjoint. Maybe not to just get the double category. You definitely need it to be a left adjoint for it to be a symmetric monoidal double category, which it is.
That's why presumably it's because it preserves co-limits, so it's.
Under coproduct.
Sorry, you guys are much faster than me. I still haven't understood
Right, I haven't finished saying, sorry. Okay, so one cells are functions, and then I'll say, so two cells are like this. Whoops. So you have two cospans, and then you have a square like this, or two squares. This is a two cell.
Such that everything commutes.
Such that, yeah, this commutes, and this comes from a function. That's a two cell. Okay, and then, so that's the idea in double categories, is you have all this data, and you can compose two cells vertically by attaching it down here, or you can compose it horizontally. Well, I didn't tell you what the composition rule was. I'll tell you that. Yeah, it's push out. Mm-hmm. Right, so you can push out. I'll just write it real quick. So if you have two open Petri nets, which are these cospans that have the codomain of one is the domain of the other, then you can write them like this and then take a push out over here.
So in particular, I could just take these cospans up to isomorphism,
Mm-hmm.
and I would get a category.
Yes.
Right?
Yep. Yeah, so
Which is something that I'm normally quite comfortable doing. Because who cares about the set theoretical identity of this particular transition? Right? So like an implementation detail, right? So
well, so what the two cells are good for is they're good for like coarse graining Petri nets. So
coarse grain.
You could do that at the bicategorical level.
you could, but the bicategory, so the reason why we use double categories instead of bicategories is because we want it to be symmetric monoidal. And symmetric monoidal bicategories are really hard, and double categories are less hard.
Double category.
In one sentence, it's a pseudomonoid in cat. No, it's a pseudomonoid in the category of double categories.
It's also really hard just to have fewer
But there's a lot, yeah,
But this is easier than a symmetric monoidal bicategory.
yeah.
What do you mean? Which one?
I think mostly Schulman
Yeah.
put together some machinery that says when you have one of these things, you can build a symmetric monoidal double category, or the axioms come for free.
Mhm.
So if you want the bicategory, this is just one convenient way to get at the bicategory.
Okay.
Yeah, so if it's vibrant is the word.
symmetric
Mhm.
and make sure things play nicely.
Is there any other reason that you prefer double category?
But this open, this construction open, this seems to be Brennan's decorated cospans.
Yeah, so there's a paper that isn't out yet, but it'll be out soon by Kenny Corser called Structured Cospans, and it's a variant of Brendan's stuff. Instead of having a decoration, we do the change in the legs instead of the apex. So,
Yeah, and Christina Vasikopoulos and Joe Moller have some results that
Mhm.
relate the two approaches.
It is, I don't understand how the two approaches, it seems to me it's the same approach.
Yeah, that's what they basically show, isn't it? But they describe exactly how it's the same, if it's
Mhm.
not clear.
yeah, and there's subtle reasons why we switched.
What happened?
So I think
There's an issue with composition, where
yeah.
it's like the things don't have to have the same name, where in decorated cospans things have to have the same name.
Okay.
There's another issue which is size.
Yeah.
There's
Right.
a size issue.
So it's actually a large set once you.
Something you could only
Uh-huh.
compose two graphs are isomorphic only if like the edge sets are actually equal, as opposed to bicheck or something like that.
But these are still sort of implementation level details that
This
Mhm.
you
doesn't deserve a new name.
Okay. All right. What was I going to just say no. All right, so that's the category. All right, I think I was going to draw a picture. Okay, so you've probably seen this picture a lot if you've seen any of John's blogs. He does a lot of these pictures. But it's a good picture. That's why it's in there. So you have a set. These are the sets, the squares. And you have elements in those sets given by these dots. And you specify the inputs and outputs of your net. Via these functions like this. And they don't have to be injective. Let's erase some of these dots. Like that, okay. And then you take the push out, you identify the things, the species over here, which have the same input. And you get, so when you take the push out, you will get a transition here. So now these two are going to get identified with this one, but these two are going to be left alone. Okay, so yeah, so you got two going out to one here, and then you get two on their own over here, and then all three of these are going into the next transition. So that's how we glue nets together. Okay. Yeah, and two cells are useful to Statebox, I think, because they want to be able to update their programs at the same time as composing them. And the coherent stuff for double categories guarantees that you can do that in a way that makes sense, sort of. Okay.
What do you mean by update?
What?
What do you mean by update programs? That you mean
So like,
change the Petri?
yeah, if you want to change the Petri net or yeah, so let's say you have like a big Petri net, and then there's a bunch of stuff going on in here, but you map it all to one transition in a different net. You want to simplify it or something. Then this would be a two-cell in our category. So this is not just one, this is like a whole net, whole subnet that I'm just leaving off. And then you could have a morphism which squashes it all into this transition.
Well, how is that a morphism of Petri? Are you saying that's a morphism of Petri nets in the sense you described?
Yeah, you'd have, not everything that squashes it will be. But
how do you get rid of, so they're in places interior to that thing, correct? When you draw that big scribble.
yeah,
Where do they get mapped to under the Petri net morphism?
that's a good question. I don't know. I don't know. Okay. But I think it still works. I'm pretty sure it works. I guess I don't have an example, but I should. But I'm pretty sure it's all right. Okay. All right, so that's the double category. And then what we do is we're going to try to construct a functor, a reachability functor from, I guess, okay, right, okay, so, yeah, this way. Okay, so we have a different way of presenting our left adjoint, which shows how Petri nets present free symmetric monoidal categories, is different from a lot of the other literature. Partially because our category Petri nets is different, But what I'm going to tell you right now is also different from what's in the paper. So, because there is a mistake in the paper. But this works. This is a fix to that mistake that I'm going to show you. Okay, so so we used to have this going into CMC, and now we're just going to have it going into its essential image, which is like in, yeah, it's in CMC.
Is that Petri or Open Petri?
Petri,
Okay.
for now.
Okay.
So what it does,
CMC.
what's CMC?
No, not CMC, but
I'll
wait, how does F go into its image? Are you
I'll define it in a second, and then it'll make sense once I tell you what it is. Okay, so you take a Petri net and you send it to a category where the objects are elements of the free community monoid. Okay, that's simple enough, right? Okay, and then, so you play the same game, except now the morphisms commute exactly. And the symmetries are the identity. So you inductively include all tensors and compositions of arrows, and subject to the axiom that f plus g is equal to g plus f for every arrow. Okay, does that make sense? I think so.
So what is CMC?
CMC,
This is just a straight functor, a monoidal functor?
this,
Yeah, well
f is the functor right now.
F is a functor.
This is a one category set.
That's a one category.
Yeah, so this is the one category of commutative monoids in cat, the one category of categories. So you can think of it like as a model. So the commutative monad lifts to a monad on cat. This is probably a complicated way to explain it. A strict monad, not a two monad, because everything's strict. So you don't worry about any. You have a commutative monoid of arrows and a commutative monoid of objects, and it's just a regular old Levier theory if you want to think of it that way as well. Does that help explain anything?
Can you explain this slide again? This board?
Yeah, so I'm not.
So
Yeah.
what are you doing? This is the semantics?
Yeah, this is our functor that, yeah, the semantics, not the whole semantics functor. This is how we,
This is for closed, semantics for closed nets.
yeah, close nets, yeah.
And so
But not rel yet,
taking
yeah.
Petri net to the free symmetrical model category generated by that Petri net.
Yeah,
No, the commutative one.
Oh, the commutative.
yeah, so instead of doing symmetrical model, we're doing
Like,
commutative.
the best DVA versus Goldsrightsy processes, right? It depends if the transition can commute without any problem, and of course, I mean, reachability is okay, causality is lost, right?
Yeah, yeah, so Montanari, I think, wrote about a similar thing, except his category of Petri nets was different. But he had a functor that was similar to this, and he talked about reachability. I think in Petri nets are monoids, he talked about this.
But why do you insist on the commutativity? This is always something really weird. I mean, also, I didn't really like it when Ugo did it, and I don't understand why you're doing it again.
So at least for me, it seems a lot more natural because this is a commutative monoid of species. So then it feels like if you replace this with a different monoid, so if you had prenets, then it should lift to a category where it's commutative. The objects are commutative in the category as well.
And moreover, if you care only about reachability, doesn't really matter who is using what.
Yeah.
Sure.
So
And with commutative now, everything starts out to be functorial, because you start with something from T to the commutative species, and then you make also the arrows commutative, and then it works. And the for each ability is fine. Makes no difference.
right. So like if you look at Sassoni's paper about his presentation functor, that's what I call these functors into categories. It's really complicated. It's a long construction, which doesn't mean it's bad, but it means you're doing something more complex than what this is. And so the reason why we're doing commutative is because it's really just like the simplest way in which Petri nets present monoidal categories. And it's
I'm not sure. It doesn't seem more simpler or more complicated to me.
But this, I mean, I could just as well, okay, if I just take sort of Petri, I take monoidal graphs, right? So I take, instead of the free commutative monoid, I just take the free monoid.
Mhm.
Then I get this functor, I get a similar functor to symmetric monoidal categories.
Yep. So yeah, so those would just be.
Commutativity doesn't seem to really do anything apart from just making life a little more difficult.
Absolutely, and I think pre-nets are better for that reason in a lot of ways, because there's a really good presentation functor from them. I think the best way to present symmetric monoidal categories that aren't strict is to start with pre-nets. And I think it's okay because like when you draw a Petri net, it has an order anyway when you draw it.
Indeed.
Yeah, even if you don't
When
admit
start
it.
drawing pictures, there's an implicit order. And
Yeah.
then okay, if you want to draw something isomorphic, that's fine. I mean, but then you at least you have in mind the isomorphism, right? Which
This is bookkeeping.
Yeah,
But I take your point.
no, but I mean,
But it's, in category theory, it's good to, I mean, it's not enough to say that things are isomorphic, you need to show the isomorphic.
Yeah. No,
I mean, he published a string of paper, I think, showing exactly how you have to mangle in order to have a commutative monoid of source, and then still being able to have a kind of reconstruction where you somehow preserve causality. And you can do that. If you are a faint of art, I would not suggest to go there.
But Fabio, this is going to YouTube, right? You know this.
I know.
So I'm going to send a relevant link.
I know that. And it's no, because
Oh, I don't think they can hear you.
because the mathematics is incredibly complex. It can be done, but of course, because you want to merge to have both things, commutative on object and not commutative on arrows. And of course, again, because you want to take care of causality. But if you want to drop causality and just discuss reachability, assume that everything is commutative. Life is so much easier than.
Yeah, this is, I guarantee you, this is like, I could write this in one sentence and describe it in one sentence. You couldn't describe Sasson's functor in one sentence. It takes a few pages at least. Yeah. Or maybe this, yeah, I mean.
Is it not just the left adjoint to some? Can you just not characterize it as left adjoint to some forgetful functor that you can write down?
There's some quotienting involved. So this U is, so how I understand it, maybe this is too much of a digression, but how I understand it is like you take a Petri net and then you take all the possible orderings of that Petri net, all the pre-nets which correspond to that Petri net, and then you use the functor on all of those pre-nets all at once.
Oh, right, because you want to use a Petri net and not a pre-net.
Yeah.
So there is an adjunction between pre-nets and symmetric monoidal categories, and then presumably this is a left adjoint between Petri nets and commutative monoidal categories.
Yeah. Yeah, so these, you get something from pre-net to, I don't know.
SMC?
So can you explain what a pre-net is?
Yeah. This is a Petri net. What should I use for a free monoid that's not commutative? Star.
Oh, so she doesn't.
That's a pre-net.
So without unit, you mean?
Without unit. Yeah, without unit.
you can have a unit, but it doesn't really make sense because I mean here there is a unit because it's a star, but I mean it doesn't really make sense to have a unit from the point of view of Petri nets because if a transition goes from 0 to something, operationally it means that it produces token without consuming anything. Doesn't really make sense.
Right, it's something you freely generate. It's not really in the data that you specify.
Why are Petri nets better than free nets? Do what?
I like pre-nets better.
The general consensus is pre-nets are better.
Well, but I don't think that's the general consensus in the world. I think most people like feature nets.
I mean, I guess if you're doing chemistry and you want like every instance of oxygen to be indistinguishable,
Yeah.
maybe you prefer Petri nets.
Because people draw systems like this, and they draw them with the idea in mind that the order doesn't matter.
But in the end, surely it's more physically correct. But I mean, two different oxygen molecules are not the same.
Isn't there an indistinguishability
Yeah.
being done at
I mean,
for oxygen it's
can I look
okay.
at this as a
But
microscope powerful enough and actually see individual chunks of oxygen?
as far as I understand, if you're working with like
That's a whole different question,
When
though.
you get down to electrons, then
yeah,
it becomes
or when you
different.
have
But for atoms, I think we're okay.
yeah, I think for atoms we're okay.
Well, okay. Anyway, all right. So that's our functor, and so Kenny has this beautiful theorem and beautiful machinery that takes all these functors and just does everything right out of the box. I don't know why I erased that. I want it there. So I'm going to erase this. Hopefully you can remember what it does. Okay, so basically what Kenny's theorem does, there's a few theorems. So what one of them does is it takes a left adjoint and it turns it into a left adjoint from two co-complete categories, and it turns it into a symmetric monoidal double category. Okay, so you've L from set to P-tree, to P-tree, and then open of P-tree is Kenny's construction applied to this functor, and all you need is that both of these sets are co-complete, and this preserves co-products. Okay, and then also we have this other functor here from P-tree to image of F. What am I going to say about this? Anyone want to guess? You're falling asleep, so.
Open image.
Yeah, open MF. We might get a better name for it. Before we had open CMC. So what's in this category? It's a double category.
Sorry, can I ask another question? What is the image of F?
Image of F, so I described this functor earlier. It makes the free monoidal category on a Petri net.
So what's the image of F?
It's the essential image of that functor. So it's the
Why?
because when it was CMC, it didn't work.
What do you mean?
It's not so.
Be a functor if you just restrict to the I don't understand. I mean, I don't understand what this even means.
So the functor worked, but it wasn't a left
Tell me that
adjoint.
this functor is dependent on the functor.
Yeah, that's.
So given that
Yeah, so-
you can take the momentum objects fully faithful factorization.
Mhm.
Yeah, but it's not. It's saying it doesn't work. Oh no, it works. It is a functor.
It is a
It's not
functor.
left adjoint, it's only a left adjoint into it.
It's only left adjoint onto its image.
Ah, okay.
So it's not F.
So it is a functor,
So
it's
it's
just not a
not
left
F.
adjoint.
Yeah.
It's not called F. It's like F. Factor F.
Well,
prime.
as well.
Yeah. So this is really confusing notation.
Yeah. Right.
And F is the original thing in the CMC, and we'll get a better name for this.
Sorry, which one's
Yeah.
which one's the left adjoint?
F hat. Okay. Okay. So this has what are the zero cells in this? Yeah. Wait. Yeah. in open of MF. I don't really tell you how it all works exactly, so I'm just relying on you to guess. So you're thinking of one cells. So like in open of Petri, the 0 cells are sets.
By definition, in open of anything, the 0 cells are sets.
So open takes as input a left adjoint from any two categories, the open construction.
So that's relevant for the 1 cells, not for the 0 cells. The 0 cells are just sets.
Yeah, the 0 cells of this one are sets because the domain of this functor is set. But the 0 cells of the domain of this functor is Petri, so the 0 cells are going to be Petri nets.
Okay, fine.
Okay. Yeah, so 0 cells are Petri nets, and then 1 cells are, what are they? You have a f hat of a Petri net over here, and you have f hat of another Petri net over here. And then up here, you have something in MF, which is just another f of another Petri net. So those are the 1 cells.
And these are commutative monofunctors.
Yes, these are all commutative monoidal functors, yeah. Mm-hmm.
It's not on the node, right? That's like your sub-isomorphism. So you're taking the essential image, not the image.
Yeah.
So the image just means if you have a presentation in terms of a Petri net. To be in this sub.
Well, I think everything is isomorphic to something in the actual. Everything is isomorphic to F.
Yes. So
It's not actually equal to F.
yeah. So maybe I shouldn't write this. I'll write C.
Yeah, what's an example of something in CMC which is not in MF?
There's okay. So
So this is the Kleisli category.
R.
of,
Oh, of course. Yeah, this is all free. Yeah, so anything not free.
Yeah. This is sort of a weird example, but
you were talking about Robin, when you move to a Kleisli category. So CMC is the Isenberg-Moore category for the
I suppose
monad on
Mhm.
cat.
yeah.
And we're just working in the Kleisli category. So maybe
Well, if F were an adjunction, we would be working in the Kleisli category.
Kleisli category for the monad on cat.
C.
The commutative monad on cat.
Yeah, but it's smaller than just the Kleisli category. MF.
I mean, it's not, in itself it's not even full, right? The functor.
Yeah, it's not full. It's faithful.
Oh yeah, it's smaller because it's just the maps that come from.
Oh,
Yeah, the maps have to come
Yeah,
from
you live
Petri net
maps, so
morphisms.
You don't have all the crazy hours.
Mhm. Okay, so there's the 1 cells, and then you can probably guess what 2 cells look like. A, right? Okay. Right, that's a bad picture, but they're these rectangles like before are the 2 cells. So these are like open commutative monoidal categories.
And what's your intuition for this open MF? How do you describe this in 3 sentences?
If you have open commutative monoidal categories, it's like you're identifying some of the objects as inputs and outputs, but they have to be the generating objects, and then you're gluing them together along those objects.
But it's not even objects, right? These are total.
Yeah, so you're right, these are not just objects.
These are like sub-computations somehow, right? So
You're right, so you're identifying subcategories in the sense and gluing along those subcategories.
where are you taking the push-up?
Uh,
In CMC?
Yeah.
And
Well-
it stays in MF?
yeah,
Okay.
That's it.
Oh yeah, because they're all maps that you lifted anyway. So it's
yeah, and
not like working in Clayzy or something where you somehow escape. They just stay in them.
yeah, so if these were allowed to be arbitrary, you wouldn't stay, but because they come from Petri net morphisms, which come from functions, you're good. Okay.
So the thing that you push out over represents computations that could happen in either Petri net, and then you push out and then you glue together the computations that sort of can run through one Petri net, then could happen in either, then could run through the other one.
I'm going to tell you an easier to understand category in a second. So like so far, you have this diagram. And then you have, right, so far we have this diagram. And then we can take the composition. And we can apply the open stuff to this whole diagram. And what we end up with is we get open a P-tree on one side. I guess we've been using these subscripts to denote the functor it comes from. Open L P-tree, and then over here we have this category here, open of MF, coming from F hat. Not enough space. Okay, so you got open P-tree. And over here you have open of MF. And this is from F hat, and this is from L. And then, wait. Oh, that's why this seemed weird. No, I should have, yeah, I should have been using the composition. F hat with L. So I told you the wrong things. These should come from sets. So these don't have any morphisms in them. Sorry about that. So this is F of L of X.
So you're just identifying objects.
Yeah. So, and that makes it easier to sort of wrap your head around. So you're really just gluing objects. Yeah, sorry, I got mixed up. Okay, so that's that category over there. And then this functor F hat induces a functor, a double functor between these two categories. And it's also a symmetric monoidal double functor. And that's all in Kenny's stuff. This induces a symmetric monoidal double functor between these two double categories.
And coming down to Earth, there would be a functor if I collapse it.
Yeah, if you take the horizontal bicategories, you get a functor. Yeah. Or horizontal bicategories and then equivalence classes of to get a category. Yeah. Okay.
So it is compositional.
Yeah. So this is the part that we were sort of talking about.
Right, but this hasn't gone to the. Yeah.
System for
Yeah,
getting
this part you
everything.
expect to be compositional because it's like this is the full semantics, right? It's the executions. So in some ways it couldn't not be compositional. Petri nets ought to be a good model for what that's describing.
Well, I think,
Sorry, what did you say? No, because there was this whole argument about composing on places like this, or composing kind of additive relations
Right.
/ transitions.
But we're not in the additive relations world. So we're not discussing
No,
this
no, I know, but
semantics. This
I'm
is the
kind of
full
surprised.
Well, the question was which was better.
That's
Yeah,
right.
it's
It's a fight.
surprised
It's a fight
that-
to the death.
Yeah.
And, but it seems like I didn't expect this to be compositional. I mean, that was my.
yeah, we were worried about that earlier, but
Mm.
it is, and it is. If we change some of the hypotheses, things break.
In fact, I was wondering why to take image of F. I mean, there isn't a junction between Petri and commutative monoidal categories, as long as you change also the arrows in Petri, because your arrows are quite narrow.
Right, and
Definition. I assume if you don't do that, it doesn't work even the definition of span, because the morphisms there are probably too general. But let's say say, that's something that I would ask.
Yeah.
Why to restrict to the faithful image when I know that there is already an adjunction?
What is it? What is the adjunction?
So
Transition allow you to get.
there's a few.
The more liberal Petrinet morphism?
Yes.
Yeah, that Montanari wrote about.
This ones you wrote about?
Hmm.
Would that allow you to look at these things as cruciates?
No.
Is that still they sound like dying to get you out.
But basically, it's like you are considering already the morphism of the Kleisler. I mean, a single place can be mapped in a multiset. Basically, that's it.
Mhm.
And then if you allow this, you basically get back. Let's say the morphism of Petrinet transition actually allowed to have just monoid homomorphism on the sorts.
Yeah, any
Instead here you are much more
homomorphism.
restricted. You map sort, single sort on single sort.
Mhm.
And then you extend, of course, to a monoid home.
Okay, so right, so this is like the semantics of open stuff, which is nice. And then to complete the semantics, we are going to map this into rel, the double categories of relations, double category of relations. So the double category relations has objects as sets. It has horizontal one cells as relations. It has vertical one cells as functions. And then two cells are all right, so if you have a relation here, which I'm going to do with this cross line, and a relation here, two cell is going to be an occlusion from F cross G. I'm
F and G are the things on the left.
Yeah, this is F and G. Okay, so it's going to be inclusion from, let me think. Yeah,
Cross G of R into R.
yeah. That's a two cell.
Yeah, but I guess the point of this operational behavior is quite powerful as well. This will push out categories.
Yeah.
Gives you all the interleaving, but
Exactly.
all possible.
Yeah,
You
exactly.
could find it's probably really one step before you go to rel as a span or something, where you keep track of all the things, and then the composition of span interleaves all the computations, and that would probably still be composition.
Right, so if you want to keep track of like causality and stuff like that, you could try to change this functor into something that's symmetric monoidal, and then forget about the second part that I'm about to tell you about. And this will give you like the semantics for open
But
nets.
usually, when you take from set to image of F, usually you require that the place which are input-output somehow in the process are just the minimal and the maximal. You don't want Apple to say to allow for input, for example, some element which is already reached by a transition or the like. Because when you compose, you lose the notion of process. And
Yeah, because you double count things. But it's okay because it's a set. But you get the same reachability relation, but sometimes there's two processes giving the same, or two processes which correspond to the same relation, element relation.
Is that what you were?
Is that what you're saying?
I understood something different.
Okay.
I think it's something. Yeah. I mean, that one is true. I mean, if I collapse from the one to relation, of course, like we say, the home set becomes flat, only one element, and everything goes. No, the fact is that usually when you have a concretely a process of a Petri nets, you have basically a string diagram, but the input and output cannot be something in the middle. Have to be always the minimal and the maximal. That's to say, the spring and the sink. While instead in the general notion of a span like that could be that actually you go to open something in the middle, so that when you do the push out could be that it's not an image of a process of a Petri anymore. Maybe. I mean, it's true.
Maybe this difference comes from the chemical motivation, like the chemical reaction network motivation rather than computation motivation. Because when you're doing chemistry, there's often that there are clear notions of sources and sinks. But
That one could be, but the fact is that, how can I say, if you look just at the process, each place in the process should be used at most once,
Right.
either as an output or by a transition. And given the generality of the cospan, it could be that actually
Right.
you're using two, and then you get something, I don't know, I should check out with an example, but actually it looks a bit peculiar because whenever you try to do cospan or the like for peternets, you restrict incredibly the kind of cospan that you can.
So if you do that, then I think you might get a functor to the reachability semantics, right? Because you don't have these loops. Is that true?
No, you just
If you restrict to
If you restrict to
do it in an obvious direction,
yeah,
that's
No.
your conjecture, right?
with a causal,
Yeah.
yeah,
Yeah, the causal ones essentially.
yeah.
Well, yeah, but
So-
is it?
So the reason why we don't use the more general morphisms is because the category with those general morphisms isn't co-complete. And we need that for these open constructions.
Two morphisms are you talking about? More general morphisms.
So you can have morphisms of Petri nets where the monoid component is any arbitrary homomorphism.
What are they?
So
The monoid homomorphism between.
Homomorphisms of the monoid of
On the free
markings, yeah.
Oh yeah, so the
Rather than
yeah, so this is not necessarily coming from a function between the species.
Yeah.
This is just any homomorphism. Okay. So this category isn't complete, or co-complete either.
Yes, self-dual.
Yeah. And we need it to be. Okay. All right, and then I guess what people were sort of talking about is that, well, I guess I haven't described this functor, but you seem to know what it does. I'll say it. What it does is so it takes one of these So remember, does this make sense as a horizontal one cell in open FL of MF? To you? Yeah, okay. So that's your horizontal one cell. So we're going to send this to the relation in n of x cross n of y. So a relation on the markings of the two nets, which I'll just say in words. So there's an element in this relation if there's a morphism. So I guess I won't say any words. I'll write it. So xy is in R. If there is a morphism from FL f of x to FL g of y in this category FP. So it's like connectivity. If they're connected in this category, then you throw that in the relation.
Where the same comment Daniel made earlier applies, that doesn't necessarily need to be the image of some P, but it's isomorphic. So, so we should be thinking of FP as just a
yeah, you're right.
monodal category.
Yeah.
Yeah, good.
So I'm sloppy about that. So maybe I'll say C and replace this with C. Yeah. But so, and we're going to end up composing these two functors anyway, so then it'll be in the image for sure because we're going to compose these. Okay. All right, and then, okay, so this isn't a functor. I've been lying to you. This is a lax functor. I guess I'll tell you what it does to two cells first. So if you have a two cell, like this. It maps to inclusion. So that's a useful fact. So you're going to get a relation on here. So that maps to a relation. N and Y. And then over down here, it'll map to another relation. And then this will give an inclusion because these maps commute essentially as Y gives an inclusion.
So it is a fun. I mean, it's a fun to rub these things. It's a double functor.
The two cells work, but the composition via pushout only maps weakly. So if you do, I'm just going to identify this one cell by the apex. So if you have like C composed with D in your category open FL of MF, then if you, I didn't name this. What should I name it? G? Okay. Then G of C composed with G of D is a subset of G of C composed with D, where this is by pushout and this is regular composition of relations. So
this is saying something about reachability, right?
yeah.
So that reachability and the composed could be, there might be ways that are not, don't come from this composition.
Yeah, exactly. Yeah, so the idea is if you have nets and then you glue them together, you've probably seen this picture. You can make loops. You can glue together loops.
Yeah, but that's why what I was saying about the fact that this string is exactly there is implicitly one direction from left to right, and if you allow to have instead the map peeking any place inside, when you compose, you can in fact add in cycles and then having some side effect like this, which you wouldn't expect actually that you would not want. So to say.
Right. So if you Petri nets like this, my drawing skills are really bad. And then, so I think this one will give a loop. Because when you compose it, you get, you've probably seen this picture before. So you get, this gets identified with this and with this, so it goes around. And then over here, you have another transition from here as well to a third one. So this is the composed net, right? Okay. So yeah, you can calculate the reachabilities, but here you can get as many tokens as you'd like because you can just keep going around. And you wouldn't be able to get that in the old one. Okay.
Are these loops the only thing that could cause this
Seems like it.
set to be strict?
It seems like it. Haven't proved anything like that.
No, I don't think so. I think you can get other, I mean, you can get like a chain.
Yeah.
Exactly,
Which has a hole in it, and you fill the hole in, for example.
Yeah. I guess I meant loop in a general sense. But yeah, you can have like something that allows you to go back where you came from and hit a transition as many times as you want.
Like the first part of the path doesn't need to come from the first component.
Yeah.
They can alternate. You can get like a zigzag.
Yeah. Okay. What else? I don't know. Questions? I think that's it.
Fabio, maybe you should say something about open veterans, like the work that you involved, like I mean the stuff with Paolo and. So what's the relationship with this? Because it seems to me very close, right?
Part of the intuition is similar in the sense that
Well, the actual structures are almost exactly